So let's try to digest some of the things that we've seen. Let's redraw our reaction that we saw for our full mechanism. So we took this, this aldehyde and we treated it with methanol, and we treated it with excess methanol. So we can either just explicitly say excess, or most often people just write excess to indicate excess methanol, and we can do this in sulfuric acid. And after losing water, we got this. This is our acetal. It fits our template for an acetal where we have an R and an H, R and H coming off of the central carbon, and then we have two, I'm going to make these R double primes for reasons that will hopefully be clear. So it fits our picture for an acetal. Note that all these reactions, acetals are pretty unstable, and if you actually treat them with water and acid, the reaction will go backwards, and you actually reform your aldehyde and liberate the two alcohols that you stuck on the molecule. This reaction works just as well with ketones. So let's say we have a methyl and a phenyl on the side of our ketone, and we react this with, let's be wild and crazy and use a different alcohol, use ethanol, and again, excess ethanol. We need an acid catalyst. We're going to lose water, and we get our same two groups on the central carbon that we started with, phenyl and methyl, and now we get this as our OR double prime group. And so here's our ketal, and this fits our template, where now we have two groups, the phenyl and the methyl here on the left-hand side of the screen, two groups, R and R prime, on our central carbon, and then some OR double prime group on these newly introduced O ethyls in this case, but OR double prime. So here's the ketal. Now, these functional groups can take a lot of different forms. So let's redraw this ketal structure, kind of the generalized structure. Put bonds in. Now, sometimes you'll see rings in these structures, and when you see these rings, I think they're rings make everything more difficult, but they're really, there's nothing new here. So what if we had these two groups connected? Well, to make that, we would need to have a ketone, start with a ketone, and we need to start with an alcohol where we have two alcohols connected by a chain. And this would be an example of this. So this alcohol, if it were to react in acid with this ketone, these two OH groups would sequentially attack at the carbonyl of the ketone. We lose water. How would we lose water? Well, we lose that oxygen as water, and we lose both of these hydrogens as water. Now, of course, we're not showing a mechanism, but if we walk through the mechanism, that's what would happen. And we get a cyclic structure that looks like this. This is a cyclic ketal. Likewise, you can have the ring appear in other forms. So let's draw this over here. We're running out of space. You could potentially have those two groups connected. And so how would you form that? Well, you'd need an alcohol. Let me see if I can pull this off. See, that'd be 1, 2, 3, 4, 5. Let's say that's an OH, and you also reacted this with methanol. And if these reacted in acid, one of the OHs would attack, the other OH could attack, we'd end up losing water, OH2, and we get to, it's going to look a little ugly. We'll end here. Let's see, let's number some carbons. That's 1, 2, 3, 4, 5. We're going to make a 5-membered ring over here. 1, 2, 3, 4, 5. And position 5 is actually an oxygen. And over here, this OCH3 will end up over here to get this. So as we get into these acetals and ketals, we're going to see we have cyclic ones and acyclic ones, but in the end, they're all the same thing. They all originated from a carbonyl, an aldehyde or a ketone, and two alcohols. Whether those alcohols are separate molecules or the alcohols are connected, it's a diol. So these are all possible ways to make acetals and ketals.